All right, so the second video here to discuss some actual calculations we'll do, and we're talking about the change of enthalpy with delta H. And so here you'll see that N comes up again, so that's the moles. H will be a constant that we'll either have to find or given to us, and the delta H, so the triangle looking shape, is the enthalpy change, usually measured in kilojoules. So here's an example. How much energy is required when 5 moles of water at 100 degrees Celsius is turned into steam at 100 degrees Celsius. So the temperature is staying the same, and we're really just changing from when it goes from liquid water to steam. And so this H value you'll find on the back of your periodic table. I'll show you in class where to find those. But you can compute this very simply by knowing the number of moles. Now, a lot of times in these types of questions, you might be asked how much energy is required when instead of 5 moles, you might have something like 100 grams of H2O, and you would have to go through the process of changing 100 grams into moles by dividing by the molar mass of water. So you will have to go through your stoichiometry reminders as you go through this unit. Now you can see here the answer for delta H is the unit of kilojoules, and there's 204 kilojoules given off from that. Now I'm going to chalk these up in terms of enthalpy changes as one of 3 things. So here the first one, we're talking about a phase change. And with a phase change, we'll use the formula delta H, so the enthalpy change is equal to moles times the constant of H. That will change for us each time we're dealing with something different. So that's the first one that we'll see. The second one that we'll see follows this type of skeleton form. So this is done without any molecules or atoms that you're familiar with, just a simple A, B, and C format. Now, this second part of the diagram, or sorry, of this enthalpy chart we're making is going to be when you do enthalpy of reactions. So here is when we're going to do an example that relies on some reaction input, and we'll be able to have to come and write something down with it. So how much energy is absorbed when we have 1 mole of A is reacting with the following? We see that the delta H, so the enthalpy change here, is 600 kilojoules. Now, in order for this to work out, we need to figure out what the constant is for each individual species, or I guess atom here. So in order for us to get the constant for A, we know that it's a 600 kilojoules for the total reaction, but there are 3 moles of A. And so, oops, sorry about that. We know there's 3 moles of A, and so therefore we know that there's 200 kilojoules per mole for A as a species. So if we were to say, plug it into the formula and figure out how much energy is absorbed when 1 mole of A is reacted, we could say that delta H is equal to 1 mole times the 200 kilojoules per mole that we previously calculated. And, oops. And so a simple example for sure, but you can also see and appreciate how there's a different stoichiometric coefficient for B. So if we say that we're looking for 1 mole of B is reacted, 1 mole B, where 600 kilojoules divided by 2 is going to equal 300 kilojoules per mole. And so we will get a different answer. So you need to make sure that when you see enthalpy for the whole reaction, to break it down for each individual species. So you can see here we have another bottom example when we're talking about a half a mole of A is reacted, where you use the same formula. Finally, here's another example. I'll just click through it so you see the combustion reaction. So this is the enthalpy of combustion that you'll have to be familiar with. And so here is the breakdown of how those will work. Now notice on the bottom how much energy is released when 10 liters of methane at STP is burned. You need to be reminded of your stoichiometry for gases as well. So you need to be pretty sharp on all of your stoichiometry stuff, so we need to practice that this week. Come and see me and I can give you a hand. And so from here, here's one final example that you can see where this time it's an endothermic reaction where it's a positive instead of a negative. So if it's a positive delta H, you know that's an endothermic reaction, and if it's negative, it's going to be exothermic, so it release heat. Now, this is the same example here, so if you have any questions about these, you can see me in class. They're pretty straightforward. And so that will kind of wrap up the reactions and the phase changes parts of enthalpy changes.